All right, so who here thinks they have a pretty good understanding from their undergraduate work of that equation in the upper left? Pretty good understanding of that already. Who recognizes that equation in the upper left? Okay. All right, so it was a little more than half. Have you studied maximum likelihood estimates? Just out of curiosity? Okay, that's great. Because, so this is I'm going to call this the IQ sub Fourier transform. And I'm guessing that the distribution of this class is somewhere here. I'm going to do a maximum likelihood estimate so that nobody's happy. No, I'm just joking. But, so I hope that if you already know the Fourier transform, that this will solidify your knowledge and give you some intuition for it, okay? So that when you hear something like that, you actually have a visual image of what's going on. And if you don't know what the Fourier transform is already, well, okay, we'll move you here, right? And you should recognize the principles, you should know some of its important properties, and have some intuition for it, okay? All right, so that warm-up shows you how important the Fourier transform is, and but I'm just showing. But it is probably the most prevalent numerical operation in signal processing, and you might say that the fast Fourier transform really helped to create the field of digital signal processing. So a transform, in very loose terms, is some form of mapping, right, between some signal, it could be a sound like you're hearing now, and some other representation of that same, but the information between the two is equivalent. They're just represented differently. Okay, that may sound very broad, but we're going to see many examples of that between a single domain, time, or space, and what we call the frequency domain. There are many, kinds of transforms, and the Fourier transform is a form of integral transform. And these are linked, just to Wikipedia. You can check them out. What we're going to spend most of our time in the next hour is talking about the Fourier transform specifically, and some special cases. The discrete Fourier transform, the fast Fourier transform, and the discrete time Fourier transform, and Fourier series, which is a special case of the Fourier transform, and I think there's a chapter in Dr. Shadmehr's book on the Fourier series. So I'm not going to spend a lot of time on that. We're really going to talk primarily about the integral transform of the Fourier equation. All right, so let's warm up a little bit more. We want to examine a relationship or a signal from an entirely different viewpoint. So, for example, this is a representation of something that has gone through some kind of weird transform. Do you recognize it? Yeah.
Is that an electoral map?
Yeah, right. It's the United States transformed such that the area of blue or red or green is in proportion to its representation in the U.S. House of Representatives. So it's proportional to population. Yeah, so there it is. It's this kind of spatial, it's still in the same domain, right? X, Y, spatial domain, but it's some kind of transformation that maybe tells you something new, right? That you couldn't really fully appreciate from this representation of that signal. Okay, here's another. This sort of changes the space in a slightly different way. This is the subway map of Manhattan, right? Shown in actual sort of X, Y coordinates on the left. You see my, yeah. And it looks kind of like a bowl of spaghetti, right? It can be a little bit hard to understand all of the connections and interconnections and so forth, especially down in this area. But a remapping of that into kind of it's not really polar coordinates, but it's a re-representation. It's a warping of that space into just this representation, which is not X, Y, but it lays things out in a way that's easier to appreciate. Some of the, let's call it signal content of this representation on the left. Okay? Here, one more example, I think. Well, yeah, actually, and this is the simplest, but maybe actually the most analogous to the Fourier transform. So if I told you to go to 39 degrees north, 18 minutes and 4 seconds, and 76 degrees west, 35 minutes and 24 seconds, you would say, well, okay, I can do that. That's a bit complicated, but I can get there. But if I told you to go to 725 North Wolf Street, right, so 725 North Wolf Street, it gets you there, but by way of a completely different domain, right? It's not latitude and longitude in the first domain. This is some other domain of street numbers and qualitative categories on streets. So it's really a different domain representation of the same point in space, which is where you're sitting right now. Okay? Make sense? So that mapping of two completely different domains is really quite analogous to what we're going to talk about now, like time domain and frequency domain, space domain and spatial frequency domain. And what we'll see is that simultaneously being able to consider a signal in either domain, right, is often the key to successful problem solving. And what the Fourier transform is doing is mapping a signal, let's say from one domain, little h of t, into a completely different representation, okay, capital H of f, new domain. And this is the transform. Okay. All right, some more examples. Here's a signal, right? And it's not that complicated. And here's a different representation of that same information by basically one number, the height of this thing. It's a number in here, right? So this is redundant information. This is just negative of that same number. So that seems pretty useful, right? It seems like I can encode a lot of information from that signal into just one number. That's pretty good. Okay, what about a little bit more complicated of a number? Here, right, a slightly more complicated signal. Now, I'm consuming a lot of information to just sort of put that in this space. But here, I just represent it by two numbers. Yeah? I think you might be starting to guess what those two numbers are. Okay, this one looks pretty darn complicated, right? Look at all this. How am I going to describe that? I can't fit a polynomial to that. Like that would be really tough. But what the Fourier transform does is it represents a domain where just, in that case, just 5 numbers are completely describing that signal. Okay, well that's magic, right? So how does it work? Can you see over here on the left? It's over there too. Here's that signal, right? And I've denoted it little h of t. So it's a time-varying function, little h, whose magnitude, right, varies in time. And now here's a bunch of functions which I've actually they're sinusoids. They're various amplitude and phase. And what the Fourier transform does is it finds what combination of amplitudes and phase sinusoids would add up to that. All right, so they're added in, right? They're added over this direction. So at a given t, right? I add up this and this and this and this, and it adds up to that number right there. And I do that for everyone, and that's right. So that's what this transform has said. There's this combination of sinusoids that gives me the original function. And if you want a really coarse analogy to that, you might. Well, here we'll come back to this in a second. See if you can figure out what I sketched on the left, or I'm sorry, on the right. So here's that idea, right? And let's look at it in terms of this equation, but let's break it down a little bit. Okay, let's understand each part of this equation and how it breaks that signal into a sum of sinusoids. Okay, well let's start by looking at the integrand. Do you want me to, well, you know what, you probably prefer that I work just on the screen, not on the chalkboard. All right. It doesn't matter? All right. Then I'm going to do it here. All right. Okay. So, well, here's one part of that integram. Okay, that's an interesting quantity. It's a complex exponential. Okay, I'll just simplify it a bit. Do you know Euler's equation? Okay, this is sort of a representation of the circle, if you will, right? Cos x, sine x, right? Sort of real and imaginary domains. Right, where a point on that circle is given by cosine x plus I sine x. So the complex exponential tells us something about sinusoids, right? So that sketch is in your lecture notes, because mine is quite sloppy. Well, what else is it? Okay, so we know that sinusoids are part of the integrand. Well, let's look at the rest of the integrand. Well, I could write that as this. So I'm sort of dividing my signal by sinusoids. Now, here is a bit of intuition I want you to hang on to for that integrand, and how to remember that there's a negative sign there, and so forth. This is like saying how many sinusoids are in this signal. Right? Like a division is sort of like a decomposition of that signal divided by this, right? Just like a normal division, or sort of. Like how many of these things, quarters, are in that thing? $1. Yeah? Yeah, totally different domain of coins, totally different domain. How many of these are in that? 4, okay. And then, the addition, I'm going to add them all up. Remember the drawing of all the cosines, right? And I add them up on, do I add them up this way? Right, no, I add them up over time, right? At a given time, I add them all up. There. So you now understand each piece of the Fourier transform, and the result is this function, well, like we saw for a single, okay, here's the domain. If h of t was a cosine, we saw it just pick out the frequency of that cosine, right? The one number. If it was a cosine sitting on top of another cosine, oh, well, there's one really large amplitude, lower frequency cosine, and then there's a little bit of a smaller amplitude, higher frequency cosine, right? So keep that picture in your mind, if you will. Whenever you see that equation, okay, keep that picture in your mind. This sort of decomposition, how many sinusoids are in this function? And when you look at a Fourier transform, or a power spectrum, or other things that are derived from the Fourier transform, you know, and this thing is plotted out in the Fourier domain, those are the weights of sinusoids of a given frequency. So that's what that function is telling you, that Fourier transform or power spectrum. How many cosines of this frequency are in, how many of this frequency, how many of this one, right? Kind of like that quotient. All right. Convention is to write lowercase letters for one domain and uppercase letters for the other domain. And specifically lowercase letters for time or space, and then uppercase for frequency. Okay, like I've done here. And so here's this is the Fourier transform, right? And this is it shown as an operator. Okay, it's just that operation. And this notation here says that these two signals are pairs, like the cosine and a delta function. Those are Fourier transform pairs, and that's what that notation is. The little double arrow. All right, so we just walked through this. Oh, here's a little bit of a different, like if I give you this complicated thing, a ticket to the Transformers monster truck pull or whatever, right? That's pretty complicated. How many of these are that? Okay, just, by way of analogy. All right, so I guess I didn't put these examples in your lecture notes, but you see this kind of thing all the time, breaking down something that's composite or complicated into simpler parts. White light is the sum of many frequencies, right? Starlight or flames, right, have frequency distributions. So this is wavelength, but this could just as easily be frequency, right? And here's this distribution of things that add up to that beautiful blue flame. Okay, now, this is a time-varying Fourier transform. We're kind of jumping to the good stuff now. Every column in this thing is a Fourier transform. For example, this. So there it is. I wrote it as power spectral density. It's the magnitude of the Fourier transform, which we'll see in a second. But this thing is telling me, right, as function frequency, how many cosines of this frequency, and this one, and this one, and this one. And then this signal changes in time, right? And the Fourier transform is changing in time. And here, just for kicks, because I think it starts right here. No, it's not starting yet. Hang on. Anybody Canadian? No? I can tell you're not Canadian because hang on. Darn. Foiled. All right. What was I pulled up the wrong one. But you wouldn't know. You're from the US. That was Hockey Night in Canada, this fight song. And what you would have heard is something that sounds like what? Here compared to here. What, do you have a feel for it yet? Lower frequency instead of higher frequency, right? So something is starting low. You see all the powers up at the up near zero. Sorry, this is high frequency. Zero's at the top. So it's starting at low frequencies. It kicks in, and you hear this kind of staccato, like high frequency stuff. And then there's kind of dips low, and then more, right? And then there's something happening here, right? At this time, right? Things drop down to low frequency again. And then the signal intensity, like if you back up and kind of blur your eyes, you see that the intensity is getting really strong here and higher frequency, and then crashes, right? Anyway. Okay, so we're warmed up, right? Oh, no, one more. We can't get enough analogy. Okay, top left, Rothko. Bottom left, Sedaghat. I just want to test your intuition here. These are spatial domain signals. This is a beautiful painting by an artist named Rothko. Another beautiful painting by a French painter named Sedaghat. These are frequency domain representations. The spatial frequency domain in F, up in X, in Y. Okay, 0 is at the center. Each of these signals peaks at low frequencies. We'll see what that means, but it means that things that are slowly varying. But they're different, right? Which is which? Which one? They're crisscrossed. So the Sedaghat is here.
Oh, no, sorry, the Sedaghat's straight.
The Sedaghat is here. And why?
Because it has a lot more high frequency stuff.
Yeah, did you hear? Yeah, it has a lot of high frequency in it, right? And so the power of that signal extends to much higher frequencies than the Rothko. All right, great. Okay, then you're all warmed up. So we should be able to put some rigor to your intuition now, okay? So we know the form of the transform, and so we should be able to solve the Fourier transform for simple functions. Like this one, for example, little h. Somebody know the name of this function? It's sort of right there. Go ahead.
Rectangular pulse.
Rectangular pulse, yeah. And then it goes by a function named rect. Okay, yeah. So there it is. It has a height a between negative t naught and plus t naught. All right, so the Fourier transform is here. So if I asked you, which I will, to write out or solve the Fourier transform of that, you should be able to do so. So let's start. Well, we start by plugging in the function, which is just a, but it only has non-zero value between minus t naught and plus t naught. So I'm just going to change the limits of integration, right? And then here's the complex exponential. Pull the a out, plug in the complex exponential. Well, sign of negative, right? It's just negative sign. There we are. Integral on the right, 0, right? Integral of sign between plus and minus limit is 0. So we're going to be left with just the one on the left. There it is. Sorry, the screen's jumping around. Integral of a cosine is sine, 1 over the argument. So the 2 pi f comes out. There we go. And evaluate the limits. I'm really drawing it out. There's that. Okay. So, are we done? No. So, I just showed you the answer. Okay, so just cancel terms, and the name of that function is a sinc, right? So so what we just showed is that the Fourier transform of a rect is a sinc. And so, pictorially, sorry, that should be flat. What does the sinc look like? You all know? Okay, so frequency domain, time domain. Fourier transform pairs. Okay, that's going to be a really useful thing. Okay, and easy to solve, right? That's an integral you can do in your head. You didn't have practically, maybe just a little bit of paper to write that out. Oh, I'm sorry. Well, here it is. All right, no more slow reveals. So there they are. The Fourier pairs of a rect and a sinc function, the amplitude relationship a to 2a t naught. Where the zeros of that sinc function lie in relation to the width of this thing, right? So the total width, you might call that like the aperture, right? Or the sampling interval. And the zeros of this sinc are at 1 over that sampling interval. That's interesting. Okay. All right, so you've done your first Fourier transform, like for real. Okay. Am I going too slow? Too slow? Get to harder stuff? What if I shifted the rect? What if it wasn't centered about 0? Would that change anything? It would, right? Yeah. And think also what we were starting with, right? How many cosines of this, how many cosines of this, how many cosines of this, and so forth. But if I, and those would add up, right, slowly to give me this perfect representation of the rect. But if I just shift this rect, let's say to just right there, yeah, and dive into the integral, what's different now? Something didn't cancel. It didn't go away. The imaginary part didn't go away. All right? I'm left with this term here. Right? Before, the imaginary term was 0, and we were just left with this sinc. The real part is the same, But somehow, just by shifting the time domain signal, I introduced an imaginary component. In general, functions are not symmetric, signals are not symmetric, right? The Hockey Night in Canada theme song is not symmetric. So in general, the Fourier transform is complex. It has a real part and an imaginary part. And that can be equivalently written as in terms of the amplitude, and again, a complex exponential. So here's some notation on real, imaginary, amplitude, right? Square root of real squared plus imaginary part squared, and what's called the phase angle, arctan of this ratio. All right, so I think one of your homework assignments asks you to solve that. But for that, just simply shifting the rect function, well, oh yeah, no, I was going to say, well, what happened here? Oh, that's interesting. I'm plotting the real part. Well, that's the absolute value of the sink, right? So it has its 0 at 1 over the sampling interval, and then it stays positive, and it just bounces down. And then look at the phase. And you should plug this in and just really start to get a little bit of a feeling. Just plug in simple values and consider why the phase, right, theta of f has this funny shape to it. All right. Oh yeah, right. So here's an asymmetric function that I've asked you to solve in your homework. You can do it. You can use a table of integrals if you like, if that's still a thing. But don't just look up the whole answer. Write it out. I want you to show your work. And it's going to have a complex part. Okay, it's going to have an imaginary part. Because that decaying exponential is one-sided. Okay, it's that function in time is 0, and then it goes up to some value, and then has an exponential decay. If it were two-sided, it would be only real, the Fourier transform, I mean. And that is a great model for the response of many physical systems in time. An amplifier, or something where there's an impulse, and then boom, the system responds in time. And of course that's not two-sided, right? The impulse happens here. If it were two-sided, that would suggest that this system responded before the impulse arrived, which is against causality, right? So a temporal response function in the time domain would tend to have these kind of one-sided responses, and it'll have complex Fourier transforms. All right, and then there's another one, which is real, because it's a symmetric function. I would just want you to do the Fourier transform of a Gaussian. A little bit harder of an integral, but you can do it, okay? All right, well, who is this Fourier guy anyway? And no one should ever pronounce it Fourier. There. He was French. He was born in 1768. He was an orphan. He was raised by Benedictine monks. At the age of 30, so he was a little bit of a political radical, and he supported the outspoken advocate of the French Revolution. At the age of 30, he accompanied Napoleon Bonaparte as a scientific advisor on Napoleon's campaign in Egypt. And we'll see that had a long-standing effect on Fourier's life. When they returned, he was appointed a prefect of a department in Grenoble. He oversaw road construction and other projects. It's interesting that he was able to do such great scientific work. I mean, he was I don't know, would you agree, Reza, a government bureaucrat of sorts?
Well, in France, up until recently,
Yeah.
you were a member of the government when you were a professor.
Okay.
All positions were government positions.
Interesting, yeah. Okay, so let's not call him a bureaucrat. He's the father of the greenhouse effect. Sort of, he didn't call it that. But in 1822, okay, there, I remember the date, he published this book, The Analytical Theory of Heat, and it was published by Fernandito. And there it is. It did three great things in that book. It laid the foundations of the Fourier transform, which Reza told me just yesterday and he said it was useless. Why would anybody ever want to add up a bunch of sinusoids to represent some other signal? So he put it in a book instead. Interestingly, one of the simplest things that you should do every time you write down an equation is to check the units on both sides of the equal sign. Sort of attributed to Fourier in some way. And then the heat equation, which I know you studied in partial differential equations. By the age of, he actually lived a reasonably long time. By 1830, he suffered a fall downstairs, which 2 weeks later resulted in the rupture of an aneurysm. Here's his tomb in Paris. You see that he decorated his tomb with these emblems of Egypt, right? And another of his great work is a monumental piece of work called The Description of Egypt. And he's one of only 72 names of great French heroes on the Eiffel Tower. There was a bronze statue erected in his hometown, but it was melted down for armaments during World War II, so the statue was lost or converted to bullets or something, casings. All right, there's a very handy table of transform pairs, some easier to solve by hand than others. Here's the rect, right? There's the sinc. We've seen that one. We're going to come back to this one in a minute. This is a triangle function, right? Centered about 0. Also with some width tau, right? And we're going to come back to that would be a little bit challenging to solve directly by way of this equation. And so we're going to see a pretty slick way of solving it. Here's your homework assignment. I'm sorry. This is your homework assignment, I think. No, this one, right? So there you know the answer. Here's the other homework assignment. Okay, so now you know the answer. So you get no points for giving the right answer, right? That's how you get there. Some other interesting ones. I think we might see these written out in the notes. A delta function is a Fourier transform pair to a constant. Now think about that for just a minute. Think about sinusoids adding up to a delta function. All right? It's pretty beautiful. That says that the delta function, you have to have equal weight of all possible sinusoids added up to give you a delta function. All right, and some others. There's an inverse. I can reverse this equation and go from the Fourier transform back to the spatial domain by an eerily familiar integral transform, right? Where all that has happened is a change in sign, right? And a change in the differential, the integral. So think about that in terms of what I said about dividing, right? Division being a decomposition of a complex signal into other parts, and now here sort of being the inverse of that, the multiplication. There's an example in your notes about the inverse Fourier transform of a constant. We just saw the forward Fourier transform of that is the delta function. Right, so that's written out here. All right. Sadly, it's not always written that way. It's not always written that way, I hate to tell you. I included the 2 pi in the complex exponential. You will find variations on this, and I've written some of them out. But they're not arbitrary, okay? There's a consistency here. So scroll to the bottom of the page in your lecture notes to see what that is. You might see the Fourier transform written this way in terms of a radial frequency, okay? But the consistency is that these little constants, these seemingly arbitrary scaling factors that are in here, where like I sort of wrote a form where it's 1, is that these products always give you 1 over 2 pi. So no matter what form you're looking at, that's the consistency among all various forms that and these factors of 2 pi get really annoying sometimes. So be careful of what are you talking about, frequency or radial frequency, and so be careful and consistent in your work, that's the consistency condition. Really is up at the top of the screen, and it amounts to a proof a principle, no matter how you write the Fourier transform, that this relationship called Percival's theorem is true, and it's to say that the energy of the signal, right, and its Fourier transform are the same. I haven't added or lost energy just by doing a transform, right? And by energy, I mean the square sum, right? Okay, that's Percival's theorem. That kind of makes sense, right? I haven't changed the amount of energy in this signal. By the way, I haven't changed the amount of information in this signal. I may have simplified its representation, but I haven't changed the amount of information content. They are equivalent. Okay, so what are some properties that this function follows, or that this transform follows? There are several really important ones that you want to know because they will help you solve problems that otherwise might be a little bit complicated and the integrals get long and difficult to solve. So, for example, let's take two time varying functions, x of t and y of t, and they have Fourier transforms capital X of f and capital Y of f, right? What if I ask you, okay, well now compute the Fourier transform of the sum of these two signals? Wondrous. You might have even guessed, but you should prove it, right? That the Fourier transform of the sum of those two signals is the sum of the Fourier transforms. And so the Fourier transform pair of that sum is the sum of the Fourier transforms. So here's an example. If I add a constant to a cosine, okay, that's kind of an interesting example, right? Well, we know that the constant has a Fourier transform pair with a delta function, and that the cosine is sort of those two we saw first. It's just it's a delta function at plus f naught, and it's a delta function at minus f naught. All right. Well, the linearity property allows you to do that very quickly, and it says that the answer is a sum of three delta functions. Yeah, I don't know that would you have known that if I had just drawn a cosine shifted up from the x-axis? You probably would have got those two delta functions, right? And said, well, there's a frequency, but would you got the other one, right? Just that simple additive shift is now just so clear because you know the first basic property of Fourier transforms, that they're linear. And so here's an illustration of that. Here's x, and here's its Fourier transform. Here's y, it's shifted. No, it's not shifted yet. Here's its Fourier transform. Here's x plus y, and there's its Fourier transform. Makes it so easy. If you can look at a function and think of it in terms of things you know, right, then calculating the Fourier transform gets a lot easier. And this is the first basic example of that. We're going to see another one in a minute. Hold tight for the convolution theorem. Okay? But remember what I said. When you can look at a signal and think of it in things that you know, like a constant and a cosine, it makes your life easier. This property will be very important in linear systems. Okay. Let's see here. Oh, okay, so more properties. There's another one called symmetry, or also sometimes called duality. Check it out. This one actually requires a little bit of thought. Scaling. This is another pretty simple one and pretty useful. And actually, we heard an example of it just before class. Okay, so remember that annoying reverberation or modulation? All right, so let's consider these two pairs, just one signal, and I'm going to scale the argument of the signal. Okay? And now I plug this in, right? And look what happens. With a little change of variable, right? The signal for that scaled argument, what did it do? It changed the argument to the Fourier transform and scaled the amplitude of the Fourier transform also. So here it scaled the amplitude, right, the 1 over k, and it scaled its argument, right, in the opposite way as I scaled the argument to the signal. So for example, and so one way to say that is that the timescale expansion, right, multiplying h of t, multiplying that argument by a number, expanding the time scale corresponds to compressing the frequency scale, right? So as something gets broader in the time domain, it gets narrower in the frequency domain. For example, a sound, right? A sound of a certain frequency expanded is a sound that's a lower frequency. Oh, you knew that already. And this is it. That's time scaling. Okay, and the amplitude changes such that Percival's theorem is preserved. It works in reverse. Frequency expansion is time contraction. And there's just some diagrams of that, right? With the rect and the sink. With the, notice the zeros of that sink, right, is always 1 over the width of that rect. Okay, so you saw this coming too, right? These zeros, as I expand that rect, we know that the zeros of the sink go as 1 over that length. So that means that the Fourier transform will compress. All right, shifting. If I shift the argument by something, yeah, well, let's look at what happens. We sort of saw an example of this earlier too, with the cosine and the sine shifting. Here, if I shifted the argument to the signal, the complex part no longer goes away, and I'm left with a complex Fourier transform. Okay. Let me skip ahead because there's some good stuff we want to get to. I mean, the rest you can pretty much read in here, and I've summarized the properties of a transform in a colorful table. Linearity, symmetry or duality, the time shift, the time scaling, and so forth. And there are others. They're summarized in that table. And I really want to save time to get to this one, where convolution of two functions, x1 and x2, right? How do I compute the Fourier transform of a convolution? All right. All right. Convolutions of two functions, a common mathematical operation. Can you name some physical process or concept that uses a convolution? Anything? Anybody? You've seen the convolution. Oh, you were gonna give a suggestion. Anything?
Filter.
Yeah, a filter. Okay. Can you what kind of filter?
Like a low pass filter, I guess you can pass a signal through it with a convolution.
Right. Yeah. That's right. So, and what you're getting at there is at the heart of linear systems, right, where I have an input to a system, I have a response function of that system, and its output is equal to its input convolved with that response function. Yeah, all of that, everything I just said is in the time domain, or space domain, I guess. There's big typos in your lecture notes on this equation here. I put that in there to keep you alert. It's because I was writing the two-dimensional one, and the x's and the t's and everything got jumbled. So, so here it is for real. This is, let's say, the first function, psi, and this is the second function, psi, and here's the response function. Okay. And you might write that convolution, and if it were two-dimensional, you might sometimes see it written with two of the little convolution symbols instead of just one. All right. There's more intuition here as well on how to compute convolutions in your head. Have you seen this before? Just like if you have, we'll go faster. If you want to spend a little time on how to do convolutions in your head, we can do that too. What do you think? Who wants to develop a little bit more intuition for the convolution? Yeah, okay, good. Then we will. All right, so let's say we've got two functions that we want to convolve, x and h, right? This might be the input to a linear system, and this might be the impulse response function. All right. We saw the convolution integral. It's right here, okay? There's two terms, x of tau, in some arbitrary time domain tau, and h of t minus tau. H of minus tau, right, this little part here, is just h of tau flipped around the y-axis. All right, the ordinate is the y-axis. So all you do is you take that h of t and you flip it. All right? We're constructing the pieces of that integral, just like we did the Fourier transform at the beginning of the class. All right, h of t minus tau is that flipped function and now just shifted by some amount t. Okay, so if I look at that integral right here, I'm going to do a flip and a shift and then a multiplication and an addition. All right, so that's my recipe. I'm going to flip, right, h of t around, h of tau around the y-axis. I'm going to shift it by some amount. I'm going to shift it by all amounts, right, because that's what's in the integral. Multiply it by x of t, or x of tau, the other function. And then I'm going to integrate, right, the area under those two. And so here's the diagram of that. Let's say that I want to convolve that rect with that one-sided exponential. Okay, h of minus tau. Okay, so here's the flip, and then I'm going to shift it by a little bit. Okay, I'm going to bring that up. I'm going to multiply the green and the blue functions, right, and then integrate the area under the, there it is. And at a certain displacement t, right, the number I get is that. And I do it for all possible values of t, and that traces out the red function. That's the convolution. Can you probably, how do you know the answer? Okay, but what if I ask you to convolve two rect functions? Can you see it? Let's say two rect functions centered on the y-axis. So the flip is just like nothing. Okay, and now I'm going to shift, and I'm going to shift it through all possible t, multiply it with that original rect, which is still sitting centered, add up the area under the two, and plot the result as a function of the shift. Can you picture it? What does it look like? Maybe a triangle. Okay, did you know the answer, or do you think it might like sweep up with a curve, or is it just like, no, it's a triangle. It's a triangle, right? Yeah, so now you can do a convolution in your head, right? Okay, so that's good. You can also do some Fourier transforms in your head, or at least you can look at a table of transforms. And so we're going to use that in just a moment on how to use the convolution in a very useful way. Let's see here. So let's talk about linear systems, okay? They are defined in ways which I think you already know. And so I'm just going to skip through, but here it is. Input to a system, impulse response function, and output. A linear time invariant, or linear shift invariant system, means that if I shift the input, then I just shift the output by the same amount. That's all that means. Okay? So for linear shift invariant systems, one of the most important principles of all time, ever, in the history of everything, really, is the convolution theorem. All right? And what that says is something that is proven right there on the page in 6 lines, is that convolution is a Fourier pair to multiplication. You see what I mean? The convolution of two functions in this domain is equal to the product of their Fourier transforms. Yeah. So a triangle function, I could say that's a triangle function. Oh, well, I know that that's actually a convolution of two rects. And I know that the Fourier transform of a rect is a sinc. That's a sinc. That's a sinc. And so that's a sinc squared. So now, without any math, just by intuition, I know that the Fourier transform of a triangle function is a sinc squared. Right? This will all be on your DBO. And there it is. That's just a simple proof of the convolution theorem. And it works in reverse. Sometimes there are reasons that I might be doing a convolution in the Fourier domain. Its counterpart in the spatial domain is multiplication. All right. So we just walked through this example in our heads, right here at the top of the next page in your lecture notes, right? And there's the math, right? And you did this Fourier transform in your head and found that the Fourier transform of a triangle function is the sinc squared. Yep. Any questions? Here's some examples for homework problem number 3. You do them all in your head. You can write them out if you want, but you don't have to. You can just do them in your head and explain how you found the Fourier transform of these products. I'm sorry, of these convolutions. Okay? Okay, so I'm going to just put this up there. There's a lot. And so does anybody have any questions? No? Am I going right down the middle of the bimodal distribution that I have hypothesized, or am I way to the left? Right down the middle. All right. I've spent all my time talking about the infinite duration, continuous domain, integral form of the Fourier transform, which we see here. I think you might know the finite duration, maybe this one, discrete domain, discrete Fourier transform. But if you look at it, you see that, for the most part, it is a discrete form of that integral transform in a fairly simple way. A summation over finite frequencies, right, of the function itself, which is finitely sampled at increments of n, complex exponential. So I don't want to be too dismissive of just, well, it's just I changed the integral to a summation. But they are, I think the analogy is clear. Okay, there's a form for the multidimensional Fourier transform. I've been talking mostly about one-dimensional time series, but images, a spatial scene in X, Y, or a volumetric scene, X, Y, and Z, or a spatiotemporal scene, X, Y, Z, and T, right? You can cast these Fourier transforms in arbitrarily many directions of however many domains you might have, and here's just the two-dimensional one, and it extends in simple ways. Okay, I want to start to get to some applications, but I want to start by saying, talking a little bit about the origin of what is maybe one of the, if not the most important development in numerical analysis of the 20th century. And I would say that the FFT. The fast Fourier transform sped the computational speed of computing a Fourier transform from order n squared, the discrete Fourier transform, n squared, the number of samples in the signal, to order 1/2 n log base 2 of n. Meaning if I had a signal that was sampled 256 times, right? This is of order 65,000 calculations by way of the FFT, 1024. So there's kind of a nice quote that says, when you speed things up orders of magnitude, the world will beat a path to your door finding applications for it. And that was really the case in 1965. It was a defense project, it was a defense project. And basically what the United States wanted to do was be able to detect very accurately when the Soviet Union was testing nuclear weapons. And the way you do that is with seismographs, right? You have sensors in the ground and you detect vibrations. All right, so you have time series and you're looking for resonant frequencies associated with echoes through the earth, right? So you're looking for this resonance that says, oh, the amplitude of this signal is such that I know something happened at this point on the earth, right, in order to create this signal here. So they needed to analyze time-varying signals, and a lot of them. And it was of national importance. And so I think it was Tukey, was the government employee, who sort of struck on the fast Fourier transform as a way of of computing that in a numerical way, orders of magnitude faster. He shared it with Cooley, who was an IBM employee, and he didn't want to tell Cooley what it was for, right? Because it was classified, I suppose, this project to detect nuclear weapons testing, or for that matter, submarines or whatever. I mean, there are so many reasons you want to have very fast analysis of complex time-varying signals. So it was never patented. And when the world realized this method, it beat a path to the door in its application. I love this though, right? Like so many things, if you look back hard enough, apparently, it all goes to Gauss, right? Who apparently struck on something resembling the fast Fourier transform in 1805, which is a pretty good trick, considering it was still 17 years until Fourier would write down the integral transform. Yeah, so clearly Gauss was doing something else, but he came up with a matrix representation of decomposition of a signal into some sinusoids of some form. Yeah. All right, so, and this is a great book, E. Oren Brigham. You can find it on Amazon. It's a little expensive. So here's one of those early applications. It's from Cooley in 1969. This was published 2 months before I was born, and it was the Rat Island earthquake, Rat Island in Alaska. So here's a seismometer reading, right when that earthquake went off. Loud rumbling. Here's the power spectral analysis of that earthquake. So like this thing should be in the Smithsonian or something, this plot here. And here's how long it would have taken to calculate that. Here's how long it would have taken to calculate that by conventional methods, 2.5 minutes. And then here's how long it takes with the FFT. All right, okay, so, okay, let's go through some applications and leave time for some questions. Okay, so and we're going to go through nothing but applications on Thursday. All right, starting with one sort of like this. A low-pass filter, you just described it, right? And here's one, there are many things that cause a low-pass filter. You might say that looking out your window, that the window is a low-pass filter. Why do I say that? What do you think? Why is the window a low-pass filter? Okay, what is that? Oh, I see how you're thinking of it. That it filters out ultraviolet light. Wow, cool. You're thinking in a totally different domain than I was thinking. Okay, so yes, I'll give it to you. But that is a low-pass filter frequencing out time-varying electromagnetic radiation, and it's filtering out the high frequency, high temporal frequency electromagnetic wave. Ah, cool answer. That's not what I thought at all. So his answer was, you look through your window and things look red. Things look redder than they are because the glass filters out blue. Okay, that's not what I was thinking, but I appreciate the answer. I was thinking in spatial domain. Why would the window be a low-pass filter on what you're seeing? Okay, wait, set that aside. What would that look like? What if I said, here's your visual scene, and now I apply a low-pass filter to it? What does that mean? Here, let's write it down real quick, just so you know what I mean by applying a low-pass filter. Right? Here's the scene. I'm going to call it h of x, right? So we're in the spatial domain. This is x, okay? And now, so what do? I apply a low-pass filter, right? So we saw that in a couple of ways previously. H of fx, spatial frequency domain. Whatever my signal is here has some Fourier transform, right? You with me? Applying a low-pass filter, transfer characteristic, a point spread in X, has a little bit of blur to it, right? An impulse, this is the impulse response. If I send the delta into the system, I get this little spread function out. It's the same on the left as the right. Isotropically blurs that signal. The output, right, image is H of X, okay, convolved with P. Therefore, here I'll make this a lowercase output, right, because we're still in this domain. And now I'll say a capital output, right, the Fourier transform of the output in the spatial frequency domain, you all still see, is what? The convolution theorem, please. Shout it out.
Multiplication.
Yeah, of what?
H of
What do you want me to call it?
P.
Big P. Okay. There. There. Okay, that's a low-pass filter. This is the low-pass filter, right? This is the Fourier transform of the impulse response, okay? Right, a very narrow function here is going to be a very broad function here. In fact, a delta function here, perfect system response, means constant transfer, passes it unchanged. Nice, incredible sense. But a window, something as simple as looking out your window, might blur the scene a little bit, right? It might convolve the scene outside with the transfer characteristic of your window pane to present the photons coming to your eye. Yeah, and so your window, in that case, your lens on the world, that filter on the world is there. It's a low-pass filter. It passes low frequencies more than high. So lenses, right, things that blur the scene. What would a low-pass filter in sound, in the time domain, or time frequency domain sound, be like? What's a low-pass filter of a time-varying signal? Bass, right. Pump up the bass, right? Low-pass filter, okay. What would a high-pass frequency be in time-varying? No, treble, yeah, treble. Treble, yeah, turn up the treble. So what would a high-pass frequency in the spatial domain look like? Huh? What is it? High-pass in space. Sharpening. Sharpening, yeah. Yeah. Or edges, right? Yeah, something that knocks out the low frequencies, the constant signal, and just leaves the high frequencies. Edges, the gradient operator. If I looked out here and I didn't see, the seats or your face or the wrinkles, I just saw the edges of everything, right? A gradient filter on the scene, yeah, high pass. All right, so here's a low pass, right? This system, we just walked through it, as a point spread function, as a transfer function, which is the Fourier transform of the impulse response. And it's generally complex, okay, right? Fourier transforms are, but the real part you probably have encountered if you took medical imaging systems is called the modulation transfer function. So if you think about it, for an imaging system, this thing here, which you call capital P, that's the modulation transfer function. And a perfect system would be a constant, a blurry system would be in the low pass. All right? Oops. That convolution where the output D equals the input convolved with the impulse response function, in imaging you might call that just the imaging equation, right? That's what imaging systems do, right? Or at least linear imaging systems do. They transfer the input to the output by way of a convolution with their impulse response. Now that's really handy, because now I can start to model linear systems in complex linear systems in a series of simple ways or cascade. So like an imaging chain, we talked about one stage, like the window. But what if there's more stuff in this imaging system? Like here's one, an objective lens and an eyepiece. Each one, light has to get through both of these to reach your eye. Oh, okay. Well, each one of these presents an aperture with a certain low pass characteristic, and so the input is cascaded through the first lens, convolved with that, cascaded with the second lens, convolved with that to give us the output. And I skipped to the answer, but the system PSF is the convolution, right, of these PSFs, like together. And the system MTF is the product of those individual transfer functions. Right? I think you can see that. You could write it down. And then 2 more examples. And then I have an appendix that's not in your lecture notes. So here's a pretty cool system. It's a little bit complicated, but not too bad. It's a lot like the 2-stage system we just saw. It's how X-ray detectors work, and that goes for CT scanners, PET scanners, fluoroscopy, right? Gamma ray telescopes in orbit around the Earth, right? They all have this basic component, which is a scintillator, usually, and then a form of optoelectronics. Okay, what is that? So I want to sense a high energy photon, like an X-ray. Well, I could grow a really, really thick semiconductor electronic to stop it, like a lot of silicon to stop this high energy X-ray, but that's really expensive. Okay, so my optoelectronics have very low sensitivity to that high energy X-ray, or they would just go right through. So I can make a scintillator. That high energy photon comes in and excites the scintillator, interacts there, and the scintillator glows, right? It emits optical photons. Oh, great, now my little optoelectronic can sense those optical photons, and I know that something happened there, right? An X-ray was incident on the scintillator there. And here's a little cutaway. The X-ray comes in, interacts in the scintillator. I get this beautiful cloud of, fluorescent or phosphorescent or scintillation photons off of the molecules of the scintillator. It just glows isotropically from the molecules that are excited and shedding optical photons now. And now that signal spreads. And, spreading, that's a low pass filter, right? And then I sense those photons as they reach this array of little photodiodes. So that's the cascade that was on the previous slide, right? There's 2 systems here. One, with a point spread function of H1, this sort of smooth blurring function of light propagating in the scintillator. And then this H2, just these little photodiode apertures, which are little rectangular optoelectronics. So I've described H2 as a rect. Well, this is the easiest one yet, right? What is the system MTF? If the PSF for H1 is a Gaussian and the PSF for H2 is a rect. Blurt it out. What is the MTF of that system? Brilliant. Yeah, you got it. You got it right. Gaussian times the sink. There's the answer to homework number 4. This one I'd kind of like you to write it out a little bit and just track the scaling factors that come along, in the Gaussian and in the rect, okay? Is it 2a or is it a over 2? And I want you to follow that through and get all the little terms right. The answer is Gaussian times sink. All right. That's kind of a funny function if you think about it, right? The Gaussian and then this sink. So that MTF is still going to have those zeros at the sink. Isn't that funny? It's kind of like the thumbprint of the square photodiodes on that system. Those zeros are still there. All right. Last example, magnetic resonance imager. Okay, on Thursday we're going to talk about other imaging systems and some time systems, and we're going to make a pair of Fourier goggles, and we're going to walk around the room in the Fourier domain. Yeah, we're going to need the phase information, by the way. If we only look at the magnitude of the Fourier transform, we'll trip on stuff. We're going to need the phase image. Okay, MRI is an imaging system which detects stuff directly in the Fourier domain. What do I mean by that? You might know already that MRI involves the body laying within a strong magnetic field, okay, so that there's a preferential direction on the magnetic moments within the body along the direction of that very strong external magnetic field. And then we pulse RF electromagnetic waves at the subject, and we excite those little magnetic moments, by which I mean protons in your body. Okay, and they excite and they lose that preferential direction, and then they sort of de-excite and realign with the magnetic field. And when they realign with the magnetic field, they give up energy, right? They absorbed energy and were knocked out of that direction, and then they realign, they relax and come back in line with the magnetic field. And when they do that, they free that energy back up again, and it's emitted as electromagnetic radiation. How long it takes them to realign depends on the environment. Oh, well, that's contrast, because if that molecule's in fat, that proton's in fat, or that proton's in bone, right? Those are going to have different relaxation times. Great. These signals are pouring out of every location in your body, and I probe those locations in your body by just measuring the received electromagnetic radiation. Very complex waveform that I break down in, for every point in your body in terms of the time, frequency domain. This is my signal in an MRI, from which I reconstruct inverse Fourier transform, right? Some measurement of the relaxation time in your body. And the map of that relaxation time in your body is what we call the MR image. Oh, isn't that amazing? Yeah, isn't that amazing? Measure these time-varying electromagnetic signals, inverse Fourier transform at every point of your body, right? The magnitude of that inverse Fourier transform has something to do with the relaxation time of the environment. That's it. I'm done. Everybody here happy with MATLAB? Everybody seeing the FFT? Right? To do your homework on Thursday, so to do tonight's homework, you already know what you need to know, and you can do it all in pen and paper, or a lot of it in your head. For Thursdays, you're going to need to write MATLAB code, okay? You're going to need to know the FFT, or more specifically, FFT2, okay? Two-dimensional discrete Fourier transform. You're going to need to know FFT shift, and you're going to need to know simple example code like this. Like if I had a noisy signal like this, here's 1D, that I could take the Fourier transform of that and I could find, you know what, I think that's 2 cosines with a bunch of background noise. Right? And you should be able to look at that power spectrum here and say, you know what, that thing is just 2 sinusoids with a bunch of background noise on top of it. And you're going to do that in 2 dimensions. So if anything I mentioned here in this appendix, which is not in your lecture notes, if any of this you're not familiar with, or if you want, like just this example code on what FFT and absolute value of the FFT and so forth, just email me and I'll send you the updated lecture note. Oh, or Dr. Shadmehr or Ehsan. Yeah, email Ehsan. I'll have sent this to Ehsan. Okay, that's it. Thank you.